So dear students, so this is third part of the stereochemistry in continuation from the of stereochemistry part, and then the in part 2 I have discussed about the types of the stereoisomerism and also the configurational isomers and conformational isomers. In detail, I have discussed about the conformations of the ethane, butane, and how to write the conformational analysis towards these two molecules, and which one is more stable. Actually, in ethane and butane, you have studied about the staggered conformation is more stable rather than the eclipsed conformation. You all come to know about some important terminology regarding the conformational analysis. So in this part of lecturing, I am going to discuss about the conformational analysis of cyclohexane. As per your syllabus, conformational analysis of cyclohexane is there. But in fact, before going to the conformational analysis of cyclohexane, we must have to have an idea about what are these cycloalkanes and how they are going to exhibit their structural property, and which type of cyclohexane cycloalkane becomes more stable, and so on. So we shall see when we go to the conformational analysis of cycloalkanes. Cycloalkanes usually they are going to represent it in the planar structures. Cycloalkanes are nothing but the cyclic hydrocarbons which are going to resemble the properties of the aliphatic hydrocarbons. That means alkanes, saturated aliphatic hydrocarbons. When we represent the molecular formula for these cycloalkanes, they are resembling with the molecular formula of alkenes, because to constitute a ring structure, we must need 3 carbon atoms. If you take cyclopropane, it has C3H6 formula. Even your propene is also having C3H6. Okay, CnH2n, CnH2n. So cycloalkanes are also having same molecular formula. They are supposed to be called as ring chain isomers. Ring chain isomers means when we write the, say for example, here I will show you the formula of the, okay, but here I could not get the pen. Okay, no problem. You know the propene molecule of CH3, CH2 double bond, CH3, CH double bond CH2, whereas cyclopropane is having CH2, CH2, CH2. There is a cyclic form. Here you will find open chain form. Chain it is cyclic. So therefore they are called as ring chain isomers. They are having same molecular formula. Most of the cycloalkanes we represent in planar structures. A simple a triangle which is going to representing that the cyclopropane it is. Here you can see this is cyclopropane, it is cyclobutane, and cyclopentane, cyclohexane. Every corner is representing methylene group. It is a CH2 group. CH2 group it is. Okay, and here also you will find C ester group, here also you will find the C ester group. So these three corners, they are representing C ester group. There are four corners, you will find four C ester group, and here five C ester group, six C ester group. In fact, these cycloalkanes are called as polymethylene. C ester group is nothing but methylene group it is. So therefore, when a group is having more number of methylene group, they are called as polymethylenes. Cycloalkanes are also called as polymethylenes. These are all having planar structure, but however, they never going to exist in the planar form. They are going to exist in the puckered or the ring structure. But in fact, I will discuss about the Bayer's strain theory and all, why they are going to exist in puckered and different orientations. The cycloalkanes are also going to exist as different staggered and eclipsed conformation. Only few conformations which are possibilities than alkanes, because ring will prevent a full 360-degree rotation. 360-degree rotations. Suppose you take a single bond and you can put any structure, it can freely rotate it. But however, when it is cyclic form, you cannot easily rotate the bond. They are undergo different rotations. Rotational motions about carbon-carbon bonds in the rings are, they are primarily back and forth rocking motion. Fourth rocking motion means ಯಾವುದಾದ್ರೂ ಒಂದು ನೀವೇ ಸ್ಪ್ರಿಂಗ್ ಟೈಪ್ ಸ್ಟ್ರಕ್ಚರ್ ಮಾಡಿ ಅದನ್ನು ಹಿಂಗೆ ರೊಟೇಷನ್ ಮಾಡಿದ್ರಿ, ಈ ಟೈಪ್ ರೊಟೇಷನ್ ಮಾಡ್ತಾ ಹೋದ್ರೆ ಅದಕ್ಕೆ ಬ್ಯಾಕ್ ಆ್ಯಂಡ್ ಫೋರ್ತ್ ರೊಟೇಷನ್ ಅಂತ ಕರಿತೀವಿ. ಸಪೋಸ್ ನನ್ನ ಕೈಗೆ ಇದೇ ಒಂದು ಬೆರಳಿಗೆ ಏನಾದರೂ ಒಂದು ರಿಂಗ್ ಸ್ಟ್ರಕ್ಚರ್ ಹಾಕಿ ಇದನ್ನು ರೊಟೇಟ್ ಮಾಡಿದರೆ ಅದು ಫ್ರೀ ರೊಟೇಷನ್. ಆಲ್ರೆಡಿ ವಿಲ್ ನೋ ದಟ್. Suppose this is going to form a ring structure like this, then you cannot easily rotate. This is one bond, this is one bond, this is one bond. There are three bonds. Of course, I am not having molecular models here. These are the three bonds. It almost looks like your cyclopentane structure. You cannot rotate easily. It's forcible in you rotate ಮಾಡ್ಲಕ್ಕೆ ಹೋದ್ರೆ break ಆಗುತ್ತೆ. Okay. So therefore, they can have the back and forth rocking motions. Geometric constraints of the ring also produce angle strain. Now, ಏನಾದರೂ forcible ಇದನ್ನು rotate ಮಾಡ್ಲಕ್ಕೆ ಹೋದ್ರೆ there must be strain in the molecule. Strain in the molecule. ನಮ್ಮದೇ ನಾರ್ಮಲ್ ಮನುಷ್ಯನ್ ತಗೊಳ್ರಿ, ಎಂದೂ ಎಕ್ಸರ್ಸೈಸ್ ಮಾಡಲಾರ್ದಂಥ ಮನುಷ್ಯ ಒಮ್ಮೆಲೆ ಯಾರ್ದೋ ನೋಡಿದ್ ನಾನು ಎಕ್ಸರ್ಸೈಸ್ ಮಾಡ್ಬೇಕಂತ ಹೇಳಿ ಒಂದ್ಸಲ ಮುಂದೆ ಬೆಂಡಾಗಿ ಮತ್ತೆ ಹಿಂದೆ ಒಂದ್ಸಲ ಬೆಂಡ್ ಆಗ್ಲಕ್ಕೆ ಹೋದಾಗ ಮರುದಿವ್ಸ 4 ದಿವಸ ಮಲಗಬೇಕಾಗತ್ತೆ ಕಂಪ್ಲೀಟ್ ಆಗಿ. ಬಿಕಾಸ್ ವಿಲ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಸ್ಟ್ರೇನ್, ಬ್ಯಾಕ್ ಪೇನ್ ಅದೆಲ್ಲ ಸ್ಟಾರ್ಟ್ ಆಗ್ತದೆ ಇಂಥವೆಲ್ಲ. ಅದೇ ರೀತಿ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಅಲ್ಲಿ ಕೂಡ ರಿಸ್ಟ್ರಿಕ್ಟೆಡ್ ರೊಟೇಷನ್ ಇದ್ದಾಗ ವಿ ಕೆನಾಟ್ ಈಸಿಲಿ ರೊಟೇಟ್ ಇಟ್. ಸೊ ದೇರ್ ಫಾರ್ ವೆರಿ ಫ್ಯೂ conformations you can find in case of the cycloalkanes, because the ring will prevent a full 360-degree rotation. In this case, if forcibly you bring about the rotation, they will produce an angle strain. They will produce the angle strain. Okay. So therefore, say for example, I will show you model here. ಏನೋ ವೈರ್ ಸಿಕ್ಕಿದೆ, ಇದನ್ನು ತಗೊಂಡು ತೋರಿಸ್ತಾ ಇದ್ದೀನಿ ನಾನಿಲ್ಲಿ. ಇದು ಒಂದು ರಿಂಗ್ ಅಂತ ತಿಳ್ಕೊಂಡು ವಿ ಕ್ಯಾನಾಟ್ ಈಸಿಲಿ ರೊಟೇಟ್ ಇಟ್. ಈ ರೀತಿ ಮಾಡ್ಬೋದು ಅಷ್ಟೇ. ವಿ ಕ್ಯಾನ್ ಈಸಿಲಿ ರೊಟೇಟ್ ಇಟ್ ಲೈಕ್ ದಿಸ್. ಅದೇ ಸಿಂಗಲ್ ಬಾಂಡ್ ಇದ್ದಾಗ ಇದನ್ನು ಹೇಗಾದರೂ ರೊಟೇಷನ್ ಮಾಡ್ಬೋದು. ಅದು ರಿಂಗ್ ಸ್ಟ್ರಕ್ಚರ್ ಇದ್ದಾಗ ಅದು ರೊಟೇಷನ್ ಮಾಡಲಿಕ್ಕೆ ಬರೋದಿಲ್ಲ. ಓಕೆ. ದ ಆ್ಯಂಗಲ್ ಸ್ಟ್ರೇನ್ ನಥಿಂಗ್ ಬಟ್ significantly it must be deviated from normal tetrahedral angle. Any molecule you can take, if it is under sp3 hybridized state having a bond angle of 109 degree 28 units, they are going to place in any corner. They are having full freedom to place the bonds or the atoms, and they will keep distance away from each other. In such case, you will not find any the strain or repulsive interaction, etc. So for example, you can take a simple methane molecule in which you will find the structure where we will find that the carbon atom in which all 4 bonds are being directed towards at the regular corners of the tetrahedron. No one atom is going to be present nearer to each other. But whereas when it is going to form a ring structure, when it is going to, this is a simple example I will show you. This is a cyclopropane. The propane it is. Just the wire ತಗೊಳ್ತಾ ಇದ್ದೀನಿ ಇಲ್ಲಿ. ಇದನ್ನು propane ಅಂತ ನಾನು ಕರಿತೀನಿ. This is CS3. Here we will find CS3. It is also CS3. Suppose if you forcibly bring all these, at this corner you will find 109 degree 28 units. Here also you will find 109 degree 28 units. But in fact, if you make a ring, then the bond is get distorted. Bond angle is get distorted. This would cause strain in the molecule. This is supposed to be a strain due to what? The angle of deviation. So it is also known to be called as angle strain it is. So therefore, a most favorable conformations of cycloalkanes which will reflect a balance between their torsional strain, steric strain, and angle strain. These 3 terms are very, very important. Torsional strain, angle strain, and steric strain. So these are very, very important. So let us see what are these strains. Angle strain, it is usually called ring strain. It is due to expansion or compression of the bonds. Just you can take my finger. If I bring it like this forcibly, it would cause a strain. If you bring it like this, it would also cause the strain. Okay, now back to forcible ittandre ಬೆರಳು ಬೇನೆ ಆಗುತ್ತೆ. Forcible ಏನಾದರೂ ಮಡಿಸ್ಲಕ್ಕೆ ಹೋದರೂ ಕೂಡ ನೋವಾಗುತ್ತೆ. This is called expansion or compression of the bond angles. Torsional strain, it is due to eclipsing of the bonds, neighboring atoms. ಎರಡು ಬೇರೆ ಬೇರೆ ಬಲ್ಕಿಯರ್ ಗ್ರೂಪ್ಸ್ ಸಮೀಪ ಇದ್ದಾಗ ಅಲ್ಲಿ ಏನು ರಿಪಲ್ಸಿವ್ ಇಂಟ್ರಾಕ್ಷನ್ಸ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. They cannot sustain or they will experience a larger repulsive force. In such case, the torsional strain occurs. Strain due to eclipsing of the bonds. ಒಂದಕ್ಕೊಂದು ಬರ್ತಕ್ಕಂಥದ್ದು ಏನು ಕಾಣಿಸ್ಲಾರ್ದಿರ್ತಕ್ಕಂಥದ್ದು eclipsing of the bonds. Then steric strain. Strain due to repulsive interactions when atoms will approach each other too closely. ಎರಡು ಬೇರೆ ಬೇರೆ ಬಲ್ಕಿಯರ್ ಗ್ರೂಪ್ ಪೂರ್ಣ ಸಮೀಪ ಇದ್ದಾಗ ಅವಾಗ ಯಾವುದಾದ್ರೂ ಒಂದು ರಿಪಲ್ಸಿವ್ ಇಂಟ್ರಾಕ್ಷನ್ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತೆ. ಅದಕ್ಕೆ ಲಾಸ್ಟ್ ಟೈಮ್ ನಾನು ನಿಮ್ಗೆ ಹೇಳಿದ್ದೆ, ಬಸ್ನಲ್ಲಿ ಇಬ್ಬರು ಸಿಂಗಲ್ ಸೀಟ್ ಅಂದರೆ 2 ಸೀಟರ್ ಮೇಲೆ ಇಬ್ಬರು ದಪ್ಪನವ್ರು ಕೂತ್ಕೊಂಡ್ರೆ ಒಬ್ಬಂದು ಕಾಲು ಒಂದು ಹೊರಗಡೆನೇ ಇರ್ತದೆ ಅವಾಗಲೇ. ಯಾಕಂದ್ರೆ ಇನ್ನೊಬ್ಬನಿಗೆ ಜಾಗ ಫುಲ್ ಆಗಿರುತ್ತೆ, ಇನ್ನೊಬ್ಬನ ಆ ಕಡೆ ಮೂಮೆಂಟ್ ಆಗಲಿಕ್ಕೆ ಬರೋದಿಲ್ಲ. ಅಂತ ಸಿಚುವೇಶನ್ ಇರ್ತದೆ. ದಟ್ ಈಸ್ ಯೂಶಲಿ ಕಾಲ್ಡ್ ಆಸ್ ಬಲ್ಕಿನೆಸ್ ಆಫ್ ದಿ ಗ್ರೂಪ್. ದಟ್ ಈಸ್ ನಥಿಂಗ್ ಬಟ್ ಸ್ಟೀರಿಕ್ ಸ್ಟ್ರೇನ್. ಅಂದರೆ ಇನ್ನೊಬ್ಬನಿಗೆ ಸ್ಟ್ರೇನ್ ಉಂಟಾಗ್ತಾ ಇರುತ್ತೆ, ಯಾಕಂದ್ರೆ ಹೊರಗಡೆ ಇರ್ತಾನೆ. ಅದೇ ರೀತಿ 2 ಬಲ್ಕಿಯರ್ ಗ್ರೂಪ್ಸ್ ಸಮೀಪ ಇದ್ದಾಗ ಅಲ್ಲಿ ಸ್ಟೀರಿಕ್ ಸ್ಟ್ರೇನ್ ಉಂಟಾಗುತ್ತೆ. ಸೊ ದೇರ್ ಫಾರ್ ಸ್ಟ್ರೇನ್ ಡ್ಯೂ ಟು ರಿಪಲ್ಸಿವ್ ಇಂಟ್ರಾಕ್ಷನ್ಸ್ ವೆನ್ ಆಟಮ್ಸ್ ಅಪ್ರೋಚ್ each other. Just you can see in a diagrammatic form. So angle strain, already I have told you, when it is get deviated from the normal tetrahedral angle it is. Okay. 2 bulkier groups are very nearer to each other. They are going to eclipsing their bonds. ಒಂದರಿಂದ ಒಂದು ಈ ರೀತಿ ಬರ್ತಕ್ಕಂಥದ್ದು. Okay. That is eclipsing of the bonds. Then steric strain. When 2 bulkier groups are very nearer to each other, largely they will experience repulsive interaction and they experience a very high amount of energy. Okay. ಅದಕ್ಕೆ ಬಸ್ಸಿಂದ ಎಕ್ಸಾಂಪಲ್ ಕೊಡ್ತೀನಿ ನಾನು ನಿಮ್ಗೆ. ಸೀಟ್ ಏನು ಸಿಗ್ಲಿಕ್ಕೆ ಅಂತಂದ್ರೆ ಒಬ್ರಿಗೊಬ್ರು ಜಗಳ ಶುರು ಆಗ್ಬಿಡ್ತದೆ. ಇದೊಂದು ದೊಡ್ಡತಿ ಮನುಷ್ಯ, ಇವೊಬ್ಬ ದೊಡ್ಡತಿ ಮನುಷ್ಯ, ಇದೊಂದು ಸೀಟ್ ಅದು. ಇಲ್ಲಿ ಇಬ್ಬರಿಗೂ ಜಗಳ ಶುರು ಆಗ್ಬಿಡ್ತದೆ. ಜಗಳ ಶುರು ಆಯ್ತಂದ್ರೆ ಬೋತ್ ಆರ್ ಬೀಯಿಂಗ್ ಬಿಕಮಿಂಗ್ ಹೈ ಪೊಟೆನ್ಷಿಯಲ್ ಎನರ್ಜಿ. ಹೌದಲ್ಲ, ಯಾರಾದ್ರೂ ಒಬ್ರು ಹೊಡ್ಕೊಂಡು ಇದಾಗಲೇಬೇಕಲ್ಲ. ಸಪೋಸ್ ಇಬ್ಬರಿಗೂ ಸೀಟ್ ಕಂಫರ್ಟೇಬಲ್ ಇತ್ತು ಅಂತಂದ್ರೆ ದೇ ಆರ್ ಅವೇ ಫ್ರಮ್ ಇಚ್ ಅದರ್, ದೇ ಆರ್ ಬಿಕಮಿಂಗ್ ಮೋರ್ ಸ್ಟೇಬಲ್. ಯಾಕಂದ್ರೆ ಇವನ್ ತಟ್ಟೆಗೆ ಇವ ಹೋಗೋದಿಲ್ಲ, ಇವನ್ ತಟ್ಟೆಗೆ ಇವ. ಅದ್ರಂಗ ಇಲ್ಲಿ ಆಟಮ್ಸ್ ಕೂಡ ವೆನ್ ಬಲ್ಕಿಯರ್ ಗ್ರೂಪ್ಸ್ ಆರ್ being very close together largely experiences the steric repulsion. Okay, so in this case high energy unstable, lower energy more stable. They are very far away from each other. Okay, in order to calculate angle strain, the German chemist John Friedrich Wilhelm Adolf von Baer, he proposed some important postulates towards the calculation of the angle strain in the cyclic molecules. For this, he also awarded the Nobel Prize. He is received in the year 1905. His name is reflected in various named reactions like Baeyer-Villiger oxidation, Bayer's reagent. I hope you heard this. It is commonly used as sodium carbonate in KMNO4 for neutral oxidation process. On von Baer nomenclature, and he granted him the Nobel Prize for the Bayer's strain theory. What we are explaining, that is calculation of the angle strain. What are these postulates? When you can take open chain hydrocarbons in which all carbon atoms are sp3 hybridized, and in the sp3 hybridized molecule, atoms are directed towards regular corners of the tetrahedron, and the bond angle between them is 109 degree 28 units. In this case, every atom or every group is far away from each other. That becomes highly stable. Suppose when we forcibly bring the bonds to united together to form a ring structure, consequently, the bond angle is no longer is equal to tetrahedral angle. Okay, so this is your propane molecule. For one carbon, one carbon, one carbon. Okay, here to here you will find 109 degree 28 units. Suppose if forcibly you bring to form a ring structure, it no longer going to exist as a tetrahedral angle. In this case, the bond angle is get deviated from 109 degree 28 units. The deviation of the bond angle from normal tetrahedral angle during formation of the ring, which produces an internal strain in the molecule. Okay, ನಮ್ಗೆ ಯಾರಾದರೂ ಫೋರ್ಸಿಬಲಿ ಬೆರಳಂತಂದು ಹಿಂಗೆ ಕೂಡಿಸ್ರಿ ಇದು ಮಾಡ್ರಿ ಒತ್ತಿದ್ರು ಅಂತಂದ್ರೆ ಅವಾಗ ಸ್ಟ್ರೇನ್ ಆಗುತ್ತೆ. ಅದೇ ರೀತಿ ಫೋರ್ಸಿಬಲಿ ನಾರ್ಮಲ್ ಪ್ಲೇನಲ್ಲಿ ಎಕ್ಸಿಸ್ಟೆನ್ಸ್ ಇರ್ತಕ್ಕಂಥ ಬಾಂಡ್ಸನ್ನು ಫೋರ್ಸಿಬಲ್ ಆಗಿ ರಿಂಗ್ ಸ್ಟ್ರಕ್ಚರ್ ಮಾಡೋ ಟೈಮ್ನಾಗ, ಯುನೈಟ್ ಮಾಡೋ ಟೈಮ್ನಾಗ ಬಾಂಡ್ ಫೋರ್ಸಿಬಲ್ ಇತ್ತಂದಾಗ ಆಂಗಲ್ ಆಫ್ ಡಿವಿಯೇಷನ್ ಅಲ್ದೇ ದ ಮಾಲಿಕ್ಯೂಲಲ್ಲಿ ಸ್ಟ್ರೇನ್ ಉಂಟಾಗುತ್ತೆ. Okay, that strain in the molecule which makes molecule unstable. Okay, thus induced strain is supposed to be called as angle strain. It is induced strain is called angle strain. The angle strain which may be defined, how to calculate this? It is nothing but half of the normal tetrahedral difference between normal tetrahedral angle and observed bond angle. This is a simple normal tetrahedral angle. Observed angle means, just you can see in the previous slide, this dotted line is indicating simple propane and existing as 109 degree 28 units. When it is forcible, bring it to form a cyclic structure, this is an observed bond angle. We can call it as a theta or alpha. Okay, so let us see. Observed bond angle is alpha. It is greater the angle strain, greater is the instability of the ring. ಹೆಂಗೆ ಬಾಂಡ್ ಆಂಗಲ್ ಡಿವಿಯೇಷನ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗ್ತದೆ, either due to compression of the bond or expansion of the bond, you will experience the strain. Higher the stability of the ring, greater would be its ease of the formation. ಯಾವ್ದಕ್ಕೆ ಸ್ಟೆಬಿಲಿಟಿ ಜಾಸ್ತಿ ಇರ್ತದೆ ಅದು ಫಾರ್ಮೇಷನ್ ಕೂಡ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. ಬಟ್ ಇನ್ ಫ್ಯಾಕ್ಟ್ larger the angle strain, larger is the instability for the molecule. Here you will find this is CS3, CS2, CS3. This is propane. And in this propane, you will find normal tetrahedral angle between any two bond cities. Even CS3, you can take carbon-carbon bond and along with the 3 hydrogens. The way you find that the normal tetrahedral angle value in this, okay, tetrahedral structure you know there. So when these two bonds come very close together, in this case, it is get deviated to 60 degree. Okay, how much it is get deviated, that we have to calculate. The two bonds are compressed by an angle of 109 degree 28 units. Then minus of 60 degree, that will comes up to 49 degree 28 units. Then half of the value, because there are two bonds which are compressed together. We can calculate how much strain is going to be exist. That is with respect to one bond. So therefore, half of the difference between normal tetrahedral angle value and observed angle. This is observed angle, normal tetra. When we calculate, this is 24 degree 44 minutes. It is supposed to be called as the angle strain. So this is how you can calculate for different set of the cycloalkanes. Cyclopropane, this is angle strain, deviation. Cyclobutane, 9 degree 44 minutes. You can apply that alpha is equal to 90 degree. Similarly, cyclohexane, minus is there. You don't confuse with this plus positive value and negative value. Negative value means it is not lower value. It means the expansion of the bond and compression of the bond. When ring size is very small, there is a bond compression. When ring size is a larger one, it is a bond expansion. Just you can compare. Here, normal tetrahedral angle value is 109 degree, 28 units. 60, 90. This is a bond compression, even up to 108. But however, when goes to greater size of the ring, you will find 120, 129. This is expansion of the bond. That's why the positive sign of an angle strain indicates that the bonds are compressed from normal tetrahedral angle value, and normal tetrahedral angle value, that is a negative sign indicates the bonds are stretched. In both the cases, molecule experiences the strain, and hence the magnitude of the angle strain determines the strain in the molecule. So whether the bond is stretched or bond is compressed. ನಾನು ನಿಮ್ಗೆ ಎಕ್ಸಾಂಪಲ್ ಕೂಡ ಕೊಟ್ಟೆ. ಎಂದೂ ಎಕ್ಸರ್ಸೈಸ್ ಮಾಡಲಾರ್ದ ಮುಂದೆ ಬಗ್ಗಿದ್ರು ಸ್ಟ್ರೇನ್ ಆಗಿ ಬ್ಯಾಕ್ ಪೇನ್ ಆಗ್ತದೆ, ಹಿಂದೆ ಸ್ಟ್ರೆಚ್ ಮಾಡಿದ್ರು ಕೂಡ ಬ್ಯಾಕ್ ಪೇನ್ ಆಗ್ತದೆ. ಜಸ್ಟ್ ಲೈಕ್ ದಿಸ್ ಫಿಂಗರ್, forcibly if you bring it like this, it will experiences the pain, and when you bring it like this, it experiences the, this is expansion, this is compression. Okay, so this is how in the molecules, when bonds are being compressed, then the positive value we will find. When the bonds are being expanded, then we will experiences the negative value. But in both the cases, there is experience of the strain in the molecule. So with this respect of the values, which one is more stable? According to postulates, larger the angle strain, higher is the instability in the molecule. Of course, cyclopropane is highly unstable compared to cyclobutane. Cyclopentane is almost 0. But when you come to cyclohexane, again 5 is greater than 0. It would be expected that cyclohexane is highly unstable than cyclopentane, and even cycloheptane is highly unstable than cyclopentane. But in fact, this Bayer's strain theory could explain only for planar rings. Planar rings, but it is not able to explain about the higher member of the rings more than 5 carbon atoms, because when size of the ring goes on increases, the carbon atoms or carbon bonds never going to exist in the same plane. We cannot easily represent the planar structure for them. They are going to exist in a puckered form. To know about this particular limitation, two co-workers, Sachet and Mohr, in the year 1918, they have proposed strainless rings. It means strainless rings, this concept, it is appearing when size of the ring is consisting of more than 5 carbon atoms. What is this stainless ring theory? Stainless ring theory is nothing but, you can see the cycloalkane, when cyclohexane is consisting of 6 carbon atoms, they become free from strain as all the carbon atoms are not forced to exist in one plane. It means when cycloalkane containing 6 or more than 6 carbon atoms, they are not forced to exist in the same plane. Hence, the atoms occupy different planes where the normal tetrahedral angle is going to retained and strain is get relieved. ಇದರ ಅರ್ಥ ಏನು? ಸೈಜ್ ಆಫ್ ದಿ ರಿಂಗ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋದಂಗೆಲ್ಲ ಬಾಂಡ್ಸ್ ಅನ್ನ ಒಂದೇ ಪ್ಲೇನ್ ಅಲ್ಲಿ ತರಲಿಕ್ಕೆ ಆಗಂಗಿಲ್ಲ. ಯಾವಾಗ ಒಂದೇ ಪ್ಲೇನ್ ಅಲ್ಲಿ ಬರೋದಿಲ್ಲ ಅಂತಂದ್ಮೇಲೆ ದೇ ವಿಲ್ ಆಕ್ಯುಪೈ ಇನ್ ಡಿಫರೆಂಟ್ ಪ್ಲೇನ್ಸ್. ಇನ್ ಸಚ್ ಕೇಸ್ ದೇ ವುಡ್ ರಿಟೈನ್ ನಾರ್ಮಲ್ ಟೆಟ್ರಾಹೆಡ್ರಲ್ ಆಂಗಲ್ ವ್ಯಾಲ್ಯೂ. When normal tetrahedral angle value is retained, in such case the molecule will not experience any kind of the strain. ಇದಕ್ಕೆ ಬೆಸ್ಟ್ ಎಕ್ಸಾಂಪಲ್ ಅಂತಂದ್ರೆ ನಿಮ್ಮ ಮನೆಗೆ ಸ್ಪಾಂಜ್ ತಗೊಳ್ರಿ. ಆ ಸ್ಪಾಂಜನ್ನು ನಾರ್ಮಲ್ ಇದ್ದಾಗ ಇಟ್ ಈಸ್ ಟೋಟಲಿ ಫ್ರೀ ಫ್ರಮ್ ಸ್ಟ್ರೈನ್, ಯಾವುದು ಸ್ಟ್ರೈನ್ ಇಲ್ಲ ಅದಕ್ಕೆ. ಯಾಕಂದ್ರೆ ನೀವು ಸ್ಕ್ವೇರ್ ಟೈಪ್ ಇದ್ರೆ ಸ್ಕ್ವೇರ್ ಟೈಪೇ ಇರುತ್ತೆ, ನೀವು ಯಾವ ಟೈಪ್ ಕಟ್ ಮಾಡಿರ್ತೀರೋ ಅದೇ ಟೈಪ್ ಇರ್ತದೆ. ಅದೇ ಸ್ಕ್ವೇರ್ ಟೈಪ್ ಇರ್ತಕ್ಕಂಥ ಸ್ಪಾಂಜನ್ನು ನೀವೇನಾದರೂ ಬೊಂಬೆ ಮಾಡ್ಬೇಕಾಗಿತ್ತಂದ್ರೆ ಅದಕ್ಕೊಂದು ಮೇಲೆ ಹೆಡ್ ಮಾಡ್ಬೇಕಾಗಿತ್ತು, ಒಂದು ರಬ್ಬರ್ ಬ್ಯಾಂಡ್ ಹಾಕೋದು, ಇದಕ್ಕೊಂದು ರಬ್ಬರ್ ಬ್ಯಾಂಡ್, ಅವಾಗ ಅದು ನಾವಾಗಿ ಅದನ್ನು ಬೇರೆ ಬೇರೆ ಸ್ಟ್ರಕ್ಚರ್ ರೂಪಲ್ಲಿ ತರ್ತಾ ಇದ್ವಿ. ಇನ್ ದಟ್ ಕೇಸ್ ಇಟ್ ವಿಲ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸಸ್ ದ ಸ್ಟ್ರೈನ್ ಅಂತ. ಸ್ಪಾಂಜ್ ವಿಲ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸಸ್ ದ ಸ್ಟ್ರೈನ್, ಬಟ್ ಆಸ್ ಸೂನ್ ಆಸ್ ಯು ರಿಮೂವ್ ದಟ್ ರಬ್ಬರ್ ಬ್ಯಾಂಡ್ it will occupy normally. All the corners will get free from that stretching. So therefore, in the same situation which will occur in the cycloalkanes which are consisting of more than 6 or more than 6 carbon atoms. When a cycloalkane is consisting of 6 or more than 6 carbon atoms, they are totally free from strain. The carbon atoms are not forced to exist in one plane. Hence, the carbon atoms occupy different planes where normal tetrahedral angle retained and strain on the ring is going to relieved. So this what we can call it as the Sachet-Mort theory or strainless ring theory. With respect to this Sachet-Mort theory, we shall learn about the conformational analysis of cyclohexane. Cyclohexane, normally we are representing simple cyclic hexagon structure, but in fact it is not like existing like that. It exists in puckered form, twisted form. One is a chair conformation, another is a boat conformation. However, chair is more stable than the boat conformation. Later we can see why it is more stable and all. When we discuss about the conformations of cyclohexane, during the existing puckered or non-planar ring, the twisting about carbon atoms, carbon bonds will result in the different conformations. The first, previously it is going to with the lower energy chair conformation. When it is going to twisted, it forms a boat. Further twisting, twist boat conformation, then half chair conformation. These 4 different situations will arise. Let us see. This is the chair conformation, more relaxed form. Now a chair mel kut relaxed. This is a more relaxed form that becomes more stable, because in the chair conformation, no one atoms are in the eclipsed situation. This is a Newman projection, what we are representing here. Okay, every atom is far away from each other. There is a CS2 group. Okay, so this is a Newman projection. This Newman projection looks like no one hydrogen atoms are in the eclipsed or nearer to each other. So therefore, this becomes more stable because it's not going to experience any internal strain or the there is no steric repulsion is also going to be present in this type of the structure. It is chair conformation of cyclohexane, which is totally free from all kinds of the strain. Of course, it is experiences the angle strain very little, but in fact, when we go for steric or torsional strain, no one strain is going to exist. All the 12 hydrogens in case of the cyclohexane, they are staggered in state. That is evident from this Newman projection here. All 12 hydrogens. 12 means 4 are from here and 4 are from here. Remaining 4 is with respect to this CS2, because you will find a cyclic structure it is. The bond angle is 111 degree, which is almost nearer to 109 degree 5 minutes. But in fact, observed angle is 120. but when it is going to exist in puckered form, the carbon atoms never going to force to exist in the same plane, so that they would retain normal tetrahedral angle value. That retained normal tetrahedral angle is not like this. It is not 109 degree 5 units, but in fact it is 111 degree. Okay, so therefore this is almost, so it is a totally free from strain. Yavagidu, when chair conformation is there. In chair conformation, all hydrogens are far away from each other. They are purely in the staggered conformation. When you go to the boat conformation, you will find that there is a torsional strain, because here every hydrogen is almost nearer to each other. This you can see the Newman projection, CS2, CS2, 6 and third carbon atom. Sixth carbon atom is here, third carbon atom is here. ಇದನ್ನ ಈ ರೀತಿ ಇದ್ದದ್ದನ್ನ ಇದು ಬೋಟ್ ಫಾರ್ಮ್ ಅಂತಾನೆ ಕರಿತೀನಿ ನಾನು. ಇದನ್ನ ಹಿಂಗೆ ಫೋಲ್ಡ್ ಮಾಡಿದಾಗ ಯಾವ ರೀತಿ ಸ್ಟ್ರಕ್ಚರ್ ಬರುತ್ತೆ ಆ ರೀತಿ ಬರುತ್ತೆ. Okay, this perspective diagram indicates that each and every hydrogen is in eclipsed conformation. Okay, for example, you can take first carbon, hydrogen here, eclipsed. Here also you will find eclipsed position. So in the eclipsed form, you will find dihedral angle is almost 0, and that is internal the repulsive interactions is very high, because when atoms are very close together, at the same time the bond angle evidently, which is, though it is 111 degree, but in fact because of the steric strain or torsional strain, it becomes highly unstable. That's why you can see here twisting about carbon-carbon single bond of the chair form results in the formation of boat conformation. Boat conformer is free from angle strain, because angle strain is remained same. However, in boat conformation, the hydrogens are eclipsed state, which causes a torsional strain in the molecule. Along with this, the hydrogen at C3 and C6 are close to each other. C3, C6 are very close to each other, but in previous case you can see they are away from each other. In the chair conformation, C3, C6 are away from each other, but here every atom is in the eclipsed conformation, even including this methylene group, and experience a larger van der Waals repulsion known as flagpole interaction. Van der Waals repulsion is called flagpole. These hydrogens are called flagpole hydrogens. Flagpole hydrogens. Flagging nindrisang hydrogen. Flagpole hydrogens. This interaction makes boat conformation is less stable. This is a very important question. Why the chair conformation is more stable than boat conformation? Explain in detail means you should explain in detail. For when it is asking for 5 mark or 4 mark question, but when it is asking for 2 mark question, in the chair conformation, every hydrogen atoms including methylene groups are in a staggered form, and there is no van der Waals repulsion, and angle of deviation, though it is remained same, because of no torsional strain in the structure, where it is becoming more stable. But whereas in the boat conformation, torsional strain is high, because C3, C6 groups are very close together. So therefore, the boat is always less stable than the chair conformation. Okay, so this already what we have seen. So these two hydrogens are called flagpole hydrogens. It is a symmetrical structure, and here this Newman projection is representing, and it is a twist boat. Just you can rotate madaraga twist boat formally varta irtade. So these are the different conformation. Least planar structure is least stable, because the observed angle is 120, and when we come to half chair, boat, twist boat, and chair conformation, so least stable, most energy, more stable, least energy. It means chair conformation is more stable conformation for cyclohexane. It is also going to reveal with respect to energy profile diagram. Here you can see the chair conformation when it is converted into half chair, it almost 22 kilojoules per mole. Then comes to twist boat, it is around 28 kilojoules per mole. Then again half chair. Then comes to lowering of energy. But in half chair conformation, here you will find 50.6 kilo. This is a very high amount of energy. And here twist boat is around 28 to 22 kilojoules. So therefore, half chair conformations are very, very unstable. Immediately they interconvert into boat and half boat, the twist boat conformation. Soon after that comes to lowering of energy. This is a chair. So because of this, lower the energy, more stable, higher the energy, unstable it is. Okay. So in the previous slide, you have seen the least stable half chair, boat, twist boat, chair. Okay. Here you can see half chair, high energy, twist boat. Twist boat is nothing but the just we can twist it like in folded form, and here half chair and then chair. So these energy factors will reveal that why chair conformation is more stable than the boat conformation. The one more important terminology which reveals about the stability of these conformations regarding cyclohexane. The hydrogens have been classified, or bonds have been classified as axial and equatorial bonds. This is an equator. Those bonds which are projecting towards this ring equator, they are called equatorial bonds. So this ball, all blue, the balls which are representing hydrogens, these are all at equators, ring equator. These are bonds called as equatorial bonds. Those are along the ring axis. They are called axial bonds. So therefore, you can see this is an equatorial hydrogen equatorial bond. In cyclohexane molecule, in the chair conformation, you will find 6 equatorial, 6 axial bonds. So all these are axial bonds. Okay. In the red mark, they are called as the axial bonds. This is an axial bond. It is an axial bond. But however, it is equatorial. It is also equatorial. Along the ring equator, idukondu draw madnodribekar. Just this comes as a ring equator it is. And along the projection towards the axial, the ring axis, that is called axial bond. These are called equatorial bonds. So that's why the chair conformation, it is represented in the two important kinds of the positions of the substituents, axial positions, equatorial positions. It has 6 axial hydrogens or axial bonds and 6 equatorial bonds or equatorial hydrogens. Okay. They are undergo some kind of flipping, where we can see that the ring flipping, which is also representing whatever you can see this equatorial bond. Soon after ring flipping, it is representing that an equatorial bond becomes axial bond. Chair conformation readily interconvert, resulting in the exchange of axial and equatorial positions by ring flip. Okay. Just ಈ ರೀತಿ ಇದ್ದಿದ್ದನ್ನ ಇದನ್ನ ಹಿಂಗ್ ಫ್ಲಿಪ್ ಮಾಡಿದ್ರೆ, just you can see this is an axial equatorial bond. This is an axial bond. Suppose if I rotate, flip, I can take. Soon after flipping, this becomes equatorial, this becomes axial. Earlier case, it is equatorial, it is an axial. Soon after flipping, this becomes equatorial, it becomes the axial. Same situation it is. So chair conformation readily interconvert, resulting in the exchange of axial and equatorial positions. Just you can see this bromine atom, it is at axial position. When ring flip is going to taking place, it becomes equatorial bond. So therefore, axial bromocyclohexane, equatorial bromocyclohexane. One thing you should remember, what are axial and equatorial hydrogens, or what are axial and equatorial bond means. In the chair conformation of cyclohexane, there are 6 equatorial, 6 axial bonds or axial hydrogens or equatorial hydrogens are there. Those which are the exist around the ring equator, along the ring equator, they are called equatorial bonds. Those which are along the ring axis, they are called as the axial bonds. Okay. So therefore, with respect to this, in the chair conformation, every equatorial axial bonds are far away from each other. That's why it is more stable. In this case, each and every bond, irrespective of that position, they are in the eclipsed form, so therefore it is the least stable. When we count for relative stabilities of the chair and boat conformations of cyclohexane, this indicates chair is more stable than twist boat, boat, half chair conformation. Examinationally, most important question is write a note on conformational analysis of cyclohexane. Means you should write the only whatever at the beginning, what I have told you, calculation of angle, strain and all, that is for knowledge purpose. With that basic knowledge, we shall explain this one. Only you can write about the conformations of cyclohexane. Okay. So this is the why and flaggable hydrogens interactions will be there. Already we have seen in the boat conformation, the two hydrogens at the bow, highest, that is in this position, the bond angle, it is bond distance is about 1.83 angstrom. This distance significantly lesser than some of the van der Waals radii, that is 2.40 angstrom unit. Okay. So with this, I will conclude about this, the conformational analysis of the cyclohexane. Okay. So in your stereochemistry topic, in these three video lecturing, part 1 purely basic aspect, part 2, part 3 are very, very important for you. And this is only what I have discussed so far in the last 2 classes. It is about conformational analysis. Okay. In the previous part 2, you have studied about conformational analysis of ethane and butane, and this is conformational analysis of the cyclohexane. Okay. I hope you understand all these aspects. Okay, once again I will repeat. This is a very important one. The axial and equatorial bonds, those which are exist along the ring equator, they are called equatorial bonds or equatorial hydrogens. Along the ring axis, they are called as the ring axial bonds are the axial hydrogens. Question ಕೇಳಿದಾಗ ಈ diagram ಹಾಕಿ ಮತ್ತು ಅದರ ಬಗ್ಗೆ ಆನ್ಸರ್ ಬರೀಬೇಕು. Okay. So with this I will conclude here, and in the next video lecturing I will discuss about the configurational isomers, especially geometrical isomerism and optical isomerism. Okay. Thank you.